All right, this is the first recorded lesson for Physics 2, and it's Lesson 1, Electrostatics. It's part of the unit Energy Conservation and Renewable Energy. These notes are in the Google Classroom, and they're on each lesson has its own notes. And then I'm going to include these video notes in case you would like me to read them for you and maybe give you a few additional explanations, particularly on some of the math type problems. So here we go. This is lesson 1, so vocabulary. Charge is the plus or minus character of an object that produces an electric field. The plus and minus signs mean they are opposite. They could have been called yes and no or up and down. So negative is not inferior in any way to positive. It just means that it's the opposite. Electrostatics is the study of stationary electrons. Stationary electrons have only an electric field. We'll talk about electric field in a moment. When electrons move, they have both an electric field and a magnetic field. Electricity is the flow of electrons from higher potential to lower potential. And it can either be an organized flow, such as an electric circuit to make an electric fan work, or it could simply be by nature, flowing from the clouds where there's a thunderstorm to the earth. Conduction is passing electrons from one object to another by direct contact. Induction is passing electrons from one object to another without the objects touching. And friction is passing electrons from one object to another by rubbing the objects together. In other words, literally rubbing off the electrons from one object to another. Electric force is the force on a charge, that is an electron or a proton, by an electric field. So when an electric field puts a force on a proton or an electron or some kind of charged particle, that's called an electric force. Electric potential, also called voltage, is how much a charged particle is being pushed. You can think of electric potential kind of like gravity. Gravity is how much pull the Earth has on an object, and electric potential is how much electrical gravity or push or pull that the electric field has on the object. Okay, electric potential energy is the amount of charge times the electric potential. So you can think of the amount of energy that an object's going to hit the ground with as being two things. How strong is the Earth's gravitational field, and how much mass does that object have? Is it a really heavy object or not a very heavy object? And those two things taken together will determine how much energy the object hits the ground with. Well, in electric potential energy, it's kind of the same thing. It's how much voltage or electric potential there is times the charge. So charge in electricity is the equivalent of mass, or how much something, how much matter something has in a gravitational field. So the more charge and the more electric potential, the more energy you're going to get. Electric field, that's the field coming out of an electrically charged object that provides a force on another electrically charged object. It's kind of like a gravitational field. Field lines are the lines that show the specific direction of an electric field around an object. As you'll see coming up here, some electric fields or some electric fields have straight field lines, and others have curved field lines. An insulator. Insulators are materials without free electrons that don't allow electricity to pass, such as rubber and glass. Conductor is materials with free electrons that allow electricity to easily pass. That could be things like metals or ionic solutions. Ionic solution would be like salt water. Salt water conducts electrons very well. We'll talk about that in a little bit. Okay, now we're on to square 2, and I break this into squares. Those simply refer to the squares you see in the Edgenuity lessons when you watch the videos. So this is the second square in the instruction section of the electrostatics lesson. Elements are pure substances that cannot be reduced to other substances. There are only 92 natural elements in the entire universe, which is kind of amazing. Protons are the positive charges. So in that diagram on the right, they're the red circles in the center, and they have a positive charge, and they're in the nucleus. And electrons are the negative charges. Electrons are the negative charges moving around the outside of the atom. Electrons in motion are what we call electricity. Finally, we have neutrons in an atom. They're the third subatomic particle, and they're neutral charges, and they have no role in electricity, so we won't even talk about them in this lesson. Okay, so there's a couple of really important principles here, or a really important principle, that like charges, I mean charges that are the same, they repel each other, and different charges attract each other. So positive repels positive, negative repels negative, those are like charges, and then opposites, positive attracts negative. Or in terms of the subatomic particles, protons repel protons, electrons repel electrons, and the two different particles, protons, attract electrons. So atoms are the smallest piece of a pure element. So there's 92 pure elements, therefore there's 92 naturally occurring kinds of atoms. Now, an important concept in electricity are ions, because they have an electrical charge. An atom with a different number of protons than electrons is called an ion. The lithium on the right loses one electron, so it has 3 protons, and those aren't shown. That's just the gray circle in the middle is the nucleus. They're in there. And then it has 2 electrons, so 3 protons, 3 pluses, and 2 electrons, 2 minuses. So that means lithium has a positive charge once it loses the electron. The fluorine atom on the right gains an electron. This creates a fluorine ion with a negative charge. So it's neutral. Atoms, they're naturally born electrically neutral, but they can gain and lose electrons. So when fluorine gains an electron, it becomes negatively charged. So positive ions are called cations, and negative ions are called anions, and what push and pull electrons to form electricity. So ions are used to really help electrons move. Since they have positive and negative charges, they will attract or repel electrons, and that's what allows them to move to form electricity. The sun and the earth produce free electrons and ions. These create electric and magnetic fields around the earth. There is one hydrogen atom for every 6 meters in space. This is why space is considered a vacuum, a place where there's nothing. That's not really an important fact. They did put it in the video, so I went ahead and included it here. Okay, now we're moving on to square 3. And in that square, they ask you a question. An oxygen atom picks up 2 additional free-floating electrons. Is the charge of the newly formed oxygen ion positive, negative, or neutral? And of course, electrons are negative, so when the oxygen takes them on, it becomes negatively charged. An electric field comes out of a charged object that can act on another charged particle. So compare the electric field to the Earth's gravitational field. The difference is that the Earth's gravitational field can only pull objects in. An electric field can either push or pull an electric charge. Electric force. So here's our first formula. A force produced by an electric field on a charged particle. Force is found from the formula F equals QE. And down below we have that. F is force, abbreviated with capital F, and it's measured in newtons. It can also be measured in pounds. When you talk about your weight is a force, and it can be measured in pounds. But in the metric system, which is all we use in science and in this class, it's going to be measured in newtons. Charge, which is Q, it should be a lowercase q, so we can change that. That's a Q. That's my way of writing a Q, so I'll write it a little better. Is measured in coulombs. That's a unit of measure for charge. And an electric field, capital E, is newtons per coulomb. So up above, your force would be the charge times the electric field. So the Earth's gravitational field attracts or interacts with the mass of your body to pull you down with a force. The force on your body caused by the Earth's gravity is called weight. So let's compare the two, because they're similar. Forces are forces, even if they seem like they're completely different. Your weight, which is a force, equals your mass times the Earth's gravitational field. And a formula you saw in the first semester of physics was weight equals mass times gravitational acceleration. An electrical force formula looks similar, except instead of mass, it interacts with electric charge. Your body would not be moved by an electric field because you're not electrically charged. So the electric force is the charge on the electrical particles, on the protons or electrons, times the electric field. So gravity field, electric field, your mass, charge, and you put those two together, you get a force from your weight or a force from an electric field. All right, we're going to move on to square 5 now. So they give you a problem, and it's a pretty straightforward plug in the numbers problem. Some of you may not be that strong at scientific notation. You should go watch the scientific notation video in all videos. It takes 17 minutes and it will teach you everything you need to know, and it will give you a couple of practice problems as well. Okay, a charge of 4.5 times 10 to the negative 5 coulombs is placed in an electric field with a strength of 2.0 times 10 to the 4th newtons per coulomb. What is the electric force acting on the charge? So the formula is up above, F equals Q times E. So you go ahead and do a multiplication of the Q and of the E. So you get 4.5 times 2.0 gives you 9.0. That's the way you do scientific notation. So you multiply these two, and then you add the exponents. So what that gives you is 4.5 times 2 is 9.0, and negative 5 plus 4 gives you negative 1. Now normally that would be an acceptable way to leave the answer, but in Edgenuity they seem to always want to convert scientific notation back to regular decimal numbers, regular non-scientific notation numbers. So what you would do is, it's a negative number, so it's going to make this number smaller. So to make this number smaller, you move the decimal to the left. And that gives you 0.9 newtons, and that's the final answer. Okay, and we move on to square 6. Electric field lines move out of a positive charge and into a negative charge. So remember that. Electric fields, just by definition, move from positive to negative. That doesn't really matter. It's not that important. Because you ask yourself, which way would an electron, which is what electricity is made up of, which way would it move in the electric field? Well, it's going to move from the negative side, or the negative charge, to the positive charge. That means it's going to move against the electric field. So the direction of electric field is really just a formality, but it is defined as moving from positive to negative, and that's why all the arrows there are pointing in that direction. So the lines come out in all directions, but they curve toward the negative charge. That's if the two charges are unlike charges. They will attract each other. Those lines that you see going off kind of into space, up above and down below, they really do actually curve around. So these would come way up here, they curve around, and they come back in to the backside of the negative charge. So they actually all do connect to the negative charge, even though in the video they say they don't. Technically they do, but in reality they do go off forever. Okay, for like charges, that is charges that are the same, they will bend away from the charge. So below, if you see directly down here, those are like charges, positive, positive. And you notice none of the lines connect to each other. They all push away from each other. They're all forcing those two charges away from each other. So these two are different charges. The lines connect. These two are similar charges, like charges. The lines do not connect. Okay, we move on to square 7. Alright, and they just give you a simple question. Use the drop-down menu to complete the statement. Based on the field lines, the electric charges indicated by the question marks are what? Are they the same or different? And since these two are not connecting, they just put question marks there, but since they're not connecting, they have to be the same charge. They're repelling each other. So the charges in this diagram are the same, so they repel. The field lines don't connect. Okay, square 8. So electric potential energy is the force on an electric charge multiplied by the distance from the source of that electric field. So potential energy, you heard that term back in Physics 1 when you talked about gravitational potential energy. And gravitational potential energy is a function of three things. The strength of the gravitational field, the Earth's gravitational field. A smaller planet like Mars would have less of a gravitational field than Earth does. It's also a function of the mass that you put in that gravitational field. You're going to have more potential energy if it's a heavier, bigger object than if it's a lighter object. And the other thing is the height off the ground. An object's going to hit the ground with more energy if you drop it from a higher place than if you drop it from a lower place. So the mass times the height times the gravitational field, and that will tell you the amount of potential energy of gravity. Well, electric potential energy is the same thing. It's force times distance. But here's the thing. We're talking about static electricity, so the object can't really move. It has to be able to move a distance in order to do some work. So it can't really move a distance, but it's potential. It's what distance it would move under this force if it were allowed to. In static electricity, think of yourself as holding the electron in your fingers inside the electric field. And it's really being pushed. It wants to get pushed out of your fingers, but it can't. You're holding it. So the electric charge has to stay in the same place. Okay, and here are the units for that last formula. Let me go ahead and write the formula again. It was U, potential energy, equals force times distance, or the distance it could move if it were allowed to. So potential energy is U, and it's measured in joules. All forms of energy, whether heat or sound or light or electrical, can be measured in joules. That's the amazing thing. All those different types of energy that seem like they have nothing to do with each other are all forms of energy and are all measured with the same unit of measure. Force is capital F, we talked about that, measured in newtons, and distance is lowercase d, and that's measured in meters. So you might remember from your last physics class that work has a formula, W equals F times d. So these two formulas look the same there. The formulas look the same, the difference is that work requires that an object move a distance d. In the potential energy equation, you are holding the charge still, that's what electrostatics means, still, static means still, so that it can't move. Potential energy tells you the amount of work that it could do if it were allowed to move. Now you can put the two equations we've just talked about together, these two equations right here, and you get U, potential energy, equals charge times electric field times distance. Okay, move on to square 10. They give you a problem to work. These are really just plug and chug problems, and I think for many of you the scientific notation is the trickiest part of this. So a charge of 4.5 times 10 to the minus 5th coulombs is placed in an electric field with a strength of 2.0 times 10 to the 4th newtons per coulomb. If the charge is 0.030 meters from the source of the electric field, what is the electric potential energy of the charge? So it's simply plugging numbers into this formula to get U. So there you have charge, electric field strength, and distance. Now let's talk about the math. First of all, you have coulombs and you have newtons over coulombs. So the coulombs cancel. You can cancel units of measure just like you cancel variables in algebra or numbers in math. And what you'll be left with is newtons and meters. And that means a newton times a meter. And that, a newton times a meter, is equal to a joule. It's the force times the distance. Okay, go back to the formula up here. It's the force, newtons, times distance in meters. So newton meter is a joule. All right, so you multiply the coefficients, 4.5 times 2.0. Now, if you have a non-scientific notation number like this, you just multiply it along with the coefficients. So 4.5 times 2.0 times 0.030, and what that will give you is 0.27 right there. And then when you multiply scientific notation numbers, you add. So let me just write this out. It's this times this times this. These three things all multiply together. And then the exponents get added together. So negative 5 plus 4 gives you negative 1. So it's 0.27 times 10 to the negative 1. Since they want you to express it as a non-scientific notation number, the negative 1 means you move the decimal to make it a smaller number. You move it in the smaller direction. That's to the left. So that's 0.027 joules. Okay, and that's that. So it's just plugging in the numbers and knowing how to handle scientific notation. Again, go back and watch the scientific notation video in all videos if you're having trouble with this. Okay, we're on to square 11. Electrical potential is called voltage, and the unit of measure is a volt. The formula is volt equals electric potential energy over charge. You don't have to memorize these formulas, but have them handy. I do have a formula sheet for you, by the way. Okay, the unit of volt is joules per coulomb, joules per coulomb, J over C. And that's how much energy you get for each amount of charge. That's what voltage is telling you. It's telling you the potential. What is the electric potential? So that's voltage. So recognize that term as being the same as voltage. What is the electric potential of a 4.5 times 10 to the negative 5 coulomb charge that has an electric potential energy of 0.027 joules? So it's simply the formula V equals potential energy over charge. Right there, again, that's a Q. So there's potential energy, there's charge. So what you do is divide this number 0.027 by 4.5, and that gives you 0.006. And then what you do is, this is just a principle of math. If you have an exponent like that in the denominator, you can move it up top to the numerator simply by changing that from a -5 to a +5. So I move it up top and make it 10 to the 5th. That's just a math principle. Okay, so I did this earlier, but let me do it again here in front of you. So what's this number going to be? Well, what you do is you write down the coefficient, and I explained this in the scientific notation video. And then you move the decimal, and you just use your common sense. Is 10 to the 5 going to make this a bigger number or a smaller number? Well, 10 to the 5th is equal to 100,000. So it's going to make it a much bigger number. So to make this bigger, rather than try to memorize right and left, you just say, I got to make it bigger, I got to move it this way. 1, 2, 3, 4, 5. You put zeros in those empty spaces. And now that you have the decimal over here, you can get rid of those zeros right there. And so the answer is 600. All right, square 13, we're moving on. A conductor allows electrons or thermal, that's heat energy, to easily flow through it. Generally, things that conduct electricity well also conduct heat well, metals in other words. Conductors have free electrons. Examples of good conductors are metals. They mention in Edgenuity videos that water is. Pure water really is not. It's not ionized. It does not carry electricity well. Where water seems to conduct electricity well and can be dangerous to step in water near an electric down power line, for example, is if it has impurities and it has metals in it. Then it can be a conductor, but pure water really isn't. And then ionic solutions. Just think of salt water. When you take salt, table salt that you eat with your meals, it's NaCl, sodium chloride. And it ionizes in water totally. That means the sodiums break into positive charges and the chlorides break into negative charges. So you have all these positive, negative charges floating around in the water, and those help electrons, which are charged, move through the water. So ionic solutions, just think of salt water, is a good conductor. Insulators are materials that do not conduct electricity or heat well. Insulators do not have free electrons. So examples of insulators are glass, rubber, or wood. So an example of both is the power cord to your computer. If you hold it, you're not going to get shocked. It has conducting material, wires inside of it, but around the outside it has either rubber or plastic coating, and that's an insulator, and that will prevent the electrons from getting out of that wire and into your hand. So that has both an insulator and a conductor. All right, and then square 14, they ask you a question. Classify each substance as either a conductor or an insulator. Sample of mercury. Mercury is a liquid at room temperature, but it is a metal, and therefore it does conduct electricity. A piece of glass, they just mentioned, that's an insulator. A rubber hose, insulator. A negatively ionized lithium paste. That sounds kind of confusing. The key word is ionized. If it has ions, that is positive and negative charges, then it would be a conductor. All right, and now we're moving on to square 16. 15 was just kind of a little introduction to the next topic. So how charges move. Friction, rubbing. The key word is rubbing. An object with electrons onto another object passes electrons. Next is conduction. Electrons move directly. That's the key word to conduction, is directly. So keyword and keyword. Electrons move directly from one object to another, such as through a copper wire or touching a rod to a charged object. And finally, induction. Electrons move indirectly. The key word is indirectly. A positively charged rod moves close to an object but does not touch it. The electrons are drawn toward the rod. Again, it's the way a fan works. The electricity comes into the fan from the wall. Now, there's power there, but how does it get across to the blade, the rotor part where the blades are turning? You can't have wires going over there, or they'll get all tangled up when the blade turns around. So the answer is they have to do it indirectly, and they pass the electrons on to that fan blade. And we'll talk about induction later with magnets. Okay, square 17. It's just kind of a little matching exercise. So conduction, that is transfer of electric charge by direct contact. There's the word direct. Induction is transfer of electric charge without direct contact, so indirect or without direct, same thing. And finally, friction, the transfer of electric charge by rubbing. The key word is rubbing. All right, and they give you one last little exercise to do here on, this is actually square 18. All right, and it says click or tap the section of the wall that will be induced with positive charge. So if you bring the positively charged balloon over, at first if you did this exercise you didn't see anything in the blue square. Then if you clicked right here on this side of the wall, that's when you saw the electrons. So the electrons will be drawn over to the positive charges even though they're not touching each other. Alright, so that concludes this lesson, the first one on electrostatics. And we'll have a lesson in the Google Classroom for each of these. If you like listening to me read them to you and go over them with you. Otherwise, you can just simply read these notes. These notes, just as you see them here, are in the Google Classroom. All right, we'll see you on the Coulomb's Law lesson.